Okay, I want to switch now to the new stuff. So we'll do a lecture on the probability, and many of these you can do. You have experiences with probability, so you can actually do some of these problems. So as we're going through it, I'll ask you to put some numbers into the chat. If you would, again, I like seeing your faces when I'm talking. So if you can at all possible, turn on your cameras. The other thing is, if you would go ahead and enter in your name right now into the chat. I just want to see who all's still with me. Okay, let's take a look at section 5.1 on probability. And so you have these handouts that are at the e-learning site. And after today, I'll post the lecture notes as well. So we're going to start off. The probability is an entire branch of mathematics. And what we're interested in is the likelihood that something would occur, and the possible values we're going to assign to that are numbers between 0 and 1. So all probabilities, no matter what context we're talking about, probabilities will always be numbers between 0 and 1. The numbers that are closer to 0 are the numbers that have a low chance of occurring. So what's the chance that Nancy Pelosi will be our next president? It's a very low probability. We've got an election coming up. What would be required at this point is that from now until inauguration, that both President Trump and Vice President Pence would have to somehow die or be incapacitated. And then the next in line would be Nancy Pelosi, the Speaker of the House. So it's a very low probability. Even lower is the probability that I would become president. While it's possible because I'm eligible, it's very unlikely. On the other side of the spectrum, you have probabilities that are very likely to happen. So anything close to 1, like 0.9, 0.99, 0.85, something like that. All of those are very likely to occur. So what's the probability that it'll rain today? Well, since it's raining most of this area here for me right now, the probability would be very high. On a spectrum, low likelihood of occurring, and then over here, high likelihood of occurring. We interpret probabilities with percentages. So if we ask, what's the probability that President Trump would be elected during the election on November 3rd, we would give the number like, right now I think it's like 0.43 or something like that. So 0.43. But when we interpret a probability like that, the way we interpret that is to convert this number into a percentage. And we say that President Trump has a 43% chance of winning the election, the 2020 election. So when you're asked for a probability, if you give this answer, it is wrong, because all probabilities are between 0 and 1. It's only when you interpret probabilities that you bring percentages into the picture. Now let's go through and take a look at number 12 here. You have 1, 2, 3, 4, 5, 6 numbers. Circle the ones that are possible probabilities. This just gets to the sense of what do the numbers look like? What are the possible ways that we can represent probabilities? I can even add some more. All right, so the question you have to ask yourself is, which of those numbers are between 0 and 1, inclusive? 0 is possible. A negative number is not. Percentage is not what we want. A number larger than 1 is not one we want. But this number, and this number, and this number are all decimal fractions that range between 0 and 1. You can even write down the decimal version of that if you want. 0.5, 0.75, 0.6667. All right, we're going to be interested in probability distributions in here. So instead of calculating just a single probability in an experiment, we're going to look at all of the different probabilities for all of the different outcomes in an experiment. And here's a feature. We have this first one that we already mentioned. By the way, we defined capital P of E as being the probability that event E would occur. So E is the event, and P is the P of E is the probability that that event would occur. Then in an experiment where you have all of the outcomes identified, if you sum up the probabilities of all the possible outcomes, you'll get 1. So here's how we would say it in words, and here's how we would say it in symbols. Sum of the probabilities must equal 1. Here's one example. Outcome, probability. And the example is to flip one coin. The outcomes are heads or tails. The probability of getting a head, there's one head, 2 possible outcomes. So the probability of getting a head would be 1 out of 2. Same thing for tails. The probability of getting a tail when you flip a fair coin. There's only one side of the coin that is a tail, and there are 2 possible sides the coin can land on, heads or tails. So 1 out of 2. And so this particular table here that we're going to call a probability distribution, when you add the probabilities of all the possible outcomes, and there are only 2 here, that the sum is going to equal 1. 1/2 plus 1/2 is 1. That's what this up here is saying. The sum of all the probabilities is 1. Another example that you're familiar with is rolling a die, a single die. That's that 6-sided number cube that has the numbers 1, 2, 3, 4, 5, 6 written on each of the 6 faces. So if we did a probability distribution for this, the outcome would be 1, 2, 3, 4, 5, or 6. When you roll a die, these are the only 6 outcomes that can occur. Then when you define all of the outcomes and their corresponding probabilities, you have the complete probability distribution. Each one of these numbers, since there are 6 of them, have a 1/6 chance of coming up on a roll, on a single roll. There's 1, 1, there's 6 total rolls. There's 1, 2, there's 6 total rolls. There's 1, 3, 6 total rolls, and so on. And if you add those together, you get 6 over 6, which is 1. So the sum of the probabilities in an experiment have to add up to 1. We'll keep coming back to this over and over and over again. All right, let's see if you, so it says, given the table, you have 1, 2, 3, 4, 5, 6. You can circle the assignments there of the ones that make up a probability distribution. So 2 things are required. Every probability has to be a number between 0 and 1. And then when you sum up all the probabilities, I'm writing shorthand math notation now, the sum of all the probabilities have to add up to 1. You need both of these 2 conditions. Let's go through them one at a time. Does assignment A, does it meet both conditions? Is every probability a number between 0 and 1? And when you add up all of those 1, 2, 3, 4 probabilities, do you get 1? You do. So, and this is tossing a coin twice. Now, most of the time, we're going to assume that the dice are, or the coins are fair. So they'll come up 50% of the time on a head and 50% of the time on a tail. And so A is really what we think of when we're flipping fair coins. However, you can weight one side of those coins so that they come up on the opposite side. So if you put the weight toward the tail side and flip a coin, it's going to land on the heavy side. So if the heavy side is the tail side, it's going to land up heads more often than tails. Okay. This one here would be one where you completely weight the head side of so tails will come up every time. But is B a probability distribution? Are all the probabilities between 0 and 1? Yes. When you add up all the probabilities, do you get 1? Yes. So that one is a probability distribution. What about C? Those are all fractions where the numerator is smaller than the denominator. And if the numerator is smaller than the denominator, then you have a number less than 1. All of those numbers are positive, so between 0 and 1. So the first one, do the sum of those 4 numbers add up to 1? Yes. 8/16 and 8/16 add up to 16/16. 16/16 is 1. What about part D? Is that a probability distribution? Now, it has to match both criteria. And so even though if you add up these numbers, you get 1, the sum is equal to 1, we can't have a negative probability. So here's the problem. So the sum is equal to 1, but the probabilities are not all between 0 and 1. So not a probability distribution. What about E? All the probabilities are between 0 and 1, but when you add those 4 numbers, the sum is less than 1. So it doesn't match that criteria, where the sum has to be exactly equal to 1. And what about the last one? All numbers between 0 and 1, 1, 2, 3, 4, 5. Yeah, that one works as well. So the sum will add up to 9/9, which is 1, and then all the probabilities are between 0 and 1. Okay, according to the American Veterinary Medical Association, the proportion of households owning a dog is 0.372. Notice this word here, proportion, coming back again. We saw relative frequency early on, and now we're going to say that a probability and a proportion are very similar as well. And then it says, what is the probability that a randomly selected household owns a dog? Well, since proportion and probability are the same, we have to write the number exactly as it appears there. Now, if they said, you know, what percent of households own a dog, we would convert that number to a percentage and say something like this. So we'd actually do the conversion. All right, I'm going further with this problem. The answer to this problem is 0.372. Proportion, probability are the same. A couple of special probabilities. If the probability is 0, that means that the event cannot happen. What's the probability if you roll a die and get a 14? Well, that's not going to happen because the only possible numbers when you roll a die are 0 through 6, or 1 through 6. So impossibility, probability equals 0. A certainty is when the probability is equal to 1. What's the probability of rolling a number less than 7 if you roll a die? Well, all of the outcomes are less than 7, so you're going to get 6 out of 6. Unusual event. Would it be unusual for someone to own a dog? Well, an unusual event is an event that has a low probability. And up here we saw that 37.2%. So it wouldn't be unusual. It's less than half of the homes own a dog, but it's not unusual. So we're going to say, for unusual, we're going to say less than 5%, or probability is less than 0.05. So we'll actually put a number to unusual in here. Is this unusual? Well, it's unusual if it would occur less than 5 times in 100. Okay, and in the probability, here's a definition. And it says in the classical, for the classical method, usually we're talking about games of chance, casino games, anything involving cards, flipping coins, rolling dice. All of those are games of chance. And we have a formula to calculate the probability. You need 2 numbers. You need the number of ways the event can occur divided by the number of possible outcomes. And so as our example, the probability of getting a head, number of ways that a head can occur, once. Number of possible outcomes when you flip a coin, 2, heads or tails. And that's where you get to 50%. So if you can identify the top number and the bottom number, you've got the probability. You just write them as a fraction. You can write them as the probability in fraction form, or you can write it in decimal form. And this is just a shorthand way, the number of events in E, the number of outcomes in E divided by the number of outcomes in the sample space. For this one, the sample space is equal to heads and tails, and the number in the sample space is equal to 2. The event is just getting ahead. The number of ways, number of elements in that event is 1. So you take the number of outcomes in the event and you divide by the number of outcomes in the sample space. So you'll be asked probabilities related to coins and probability related to dice. And then we're going to be calculating, because this is statistics, we're going to be looking at frequency distributions and calculating probabilities out of frequency distributions. So here's another formula. This is for empirical probabilities, and these are based on frequency distributions, same ones we calculated earlier in the course. Whenever you see the word empirical, that means related to data. So if that is an empirical question, that's a question that can be answered by going out and collecting data. We can answer that empirically, well, because there's data out there that would lead us to the right conclusion. All right, let's take a look at number 28. In a survey of 1,100 female adults, it was determined that 341 volunteered at least once in the past year. So the number of trials, in this case, would be the number of respondents. And they tell us that this is 1,100. The frequency of E would be the number who volunteered. So the probability of the event is the frequency, number who volunteered, which is 341, and then you divide that by the 1,100. So it's like a relative frequency. That's what probability is. And particularly when we're doing probabilities in an empirical setting where we have a frequency distribution. Most empirical probabilities we are going to interpret with the decimal version. So I'm going to take 341 and divide by the 1,100, and that's 0.31. Pay particular attention in this section, at least in the homework, where they're going to tell you to round to a nearest number of decimal places. So they'll be very picky about decimal places in this section. Interpret the probability. So the way we interpret probabilities is with percents. So we would need to convert that number to a percent, at 0.31, move the decimal point 2 places to the right, and then affix the percent symbol. And we would say like this: 31% of female adults volunteered at least once in the past year. Some of these problems will give you the frequency distribution, and you have to calculate the corresponding relative frequency. This is a problem back in the first week of class we did this. Find the frequency distribution. If you have the frequency distribution, find the relative frequency distribution. Well, it turns out that the relative frequency is exactly, in this setting, the probability. So we're going to calculate it in the same way. Do they tell us how many were involved? They don't. So first thing you have to do is to add up all these frequencies to get the sample size, and that's 4521. How often do you wear a seatbelt? You know, you can see most of the time, overwhelming amount of the time, that folks always wear their seatbelt, but there are some who never wear their seatbelt, some most of the time. So this is what they asked college students, and this is what it came out to be. So we take each one of those frequencies and divide by the total, and then convert it into a decimal. And I'll write down 3-place decimals. If they say just give me the answer in fraction form, well, we're done with the problem. But usually for these probabilities like this, in the empirical setting, they're going to ask us for the decimal version. And so you can see with this last probability, the response always, we can say, you know, over 2/3 of the time, college students always use their seatbelt. Because 2/3 of the time would be 66%, right? 66 and 2/3. All right, so when they ask for a probability model, you have to have the response, the outcome, and you have to have the probability. And in this table, they only gave us the frequency and not the probabilities. So we had to add this next column here in order to get the probability model. All right, so this piece right here is what they wanted in part A. And Then they ask us a question where they use that word unusual. Is it unusual? Well, now we have a rule of thumb. Unusual means less than 5% of the time. So is it unusual for a college student to never wear a seatbelt when driving a car? So we go up to never, go over to the percentage or the decimal. The probability is 0.026. This number is less than 0.05, which is 5% of the time. And so since college students never wear their seatbelt 2.6% of the time, or I should say that 2.6% of college students never wear a seatbelt, that's less than 0.05. So yes, it is unusual for a college student to never wear a seatbelt. The probability is 0.026, which is less than 0.05. Okay, and let's take a look at number 48, one last problem in this section. We have three different types of probability, three types. One was the classical, and that was defined earlier. It's related to if we know all the outcomes, we know them all, particularly in games of chance, we know all the possible outcomes. Number two is the empirical probability. This is the one where we're going to be using some kind of data. So like our previous example up here with the seat belts, all based on data. They did a survey of 4,500 students, asked them, how often do you wear a seatbelt? The third kind is a subjective probability. This is something that weather people do. They use all the facts at hand. It could be an educated guess, but they predict the chance that it's going to rain or snow or have sun on a particular day. So it's subjective. It's a probability based on personal judgment, and that could be very informed personal judgment. So classical, empirical, or subjective. Classical, empirical, or subjective. Multiple choice. The probability of having 8 girls in an 8-child family is that number. Do you think that's classical, where we know the outcomes, all the outcomes? Is it empirical? Is it based on data? Or is it subjective? I'll do a calculation here. 0.5, which is the probability, let's say, of having a boy or a girl. It's about 50-50. If we raise that to the 8th power, we get this number. And that is precisely the number that they have here. So this is a classical. It's not based on collecting data where they went out and they have a frequency table in a given area where they say, okay, there were 700 boys and 700 girls, and then base it on that way. This is actually a mathematical formula, 0.5 to the 8th power. Okay, next one, part B. On the basis of a survey of 1,000 families with 8 children, the probability of a family having 8 girls is this. So you can compare these two numbers, 0.0039 versus 0.0054. But this one, part B, is based on a survey. So what do you think? Empirical, classical, or subjective on this one? Someone just making an educated guess? Do we actually know all the possible outcomes like this? Or is it based on data? Yep, based on data, so we'll call this one empirical. As soon as they say it's based on a survey, that implies that they're going to go out and collect some data. And they're going to make their conclusions based on the results or the summary statistics that they get from the data. Okay, let's move on. According to a sports analyst, the probability that the Chicago Bears will win their next game is about 0.30. Which probability is that? Empirical, classical, or subjective? Subjective. It could be based on some inside information. It could be based on what this analyst knows about these teams. It could be a very educated guess. But ultimately, when the game comes down, we don't know who's going to win. And so it's just somebody's opinion at this point. It could be an educated guess, but still an opinion. Okay, D, on the basis of clinical trials. We have a lot of clinical trials going on right now with COVID vaccines, phase 3 trials. The probability of efficacy, effectiveness of a new drug is 0.75. Classical, empirical, subjective on that last one. Yes, empirical. So what they do is they ask, say, 1,000 individuals to, and they test them to make sure that they don't have the coronavirus, nor never had the coronavirus. And then they put 500 in one group where they administer the new vaccine, the one that they think works. And then they put the other 500 in a different group, and then they do these double-blind studies. So they have these medical assistants, doctors, nurses, whatever. They go for all 1,000 patients, the 500 that are getting the vaccine, and the 500 who are getting what we call a placebo, a fake drug. And they give the doctors or the medical people, they don't know what they're giving to the patients, and the patients don't know what they're receiving. So it's called double blind. You know, if they had a doctor that said, hey, I think this is going to work for you, you know, they don't want to be in that situation. So the doctors don't even know what patients are receiving what med, the new vaccine or the placebo. And then at the end, they subject these individuals to the coronavirus, and they see which group, what percentage in each group get infected. And if the vaccine works, then they should have fewer infections in the vaccine group than they do in the other groups. I don't even know if that's ethically correct to do that, but you get the idea. All right, so that's kind of a overview and of probability, a real intro. We do have more complicated events that we're going to be calculating, and some of them involve a combination of events. And so we have some properties that help us to calculate these compound events, and they appear in this next section, 5.2. All right, so what I'll do is give you the results, and then we'll look at a couple of problems. So this whole section here, and really all you have are two results. There's this result, and there's this result. One is the complement rule, and one is the general addition rule to calculate the probability of E or F. E or F. So a compound event, and we have two events, E and the other event, F, and we're interested to ask the question, what's the probability that both of those two things will occur at the same time? And here's what this works out. I'll do a Venn diagram here. You have E is one event, and you have F, which is the other event in here. Notice they have something in common. They have an intersection here. So if we wanted the probability of E or F, E or F would be this region here. For E or F, we mean one or the other or both. So it would involve all the red shaded region inside both circles. And the way this formula says we're going to calculate it is this. We're going to take the probability of E, which is all of this, and we're going to add to that the probability of F, which is all of this. Just going to shade in the F circle here, the F event. But you'll notice that by shading both of those full circles there, those full events, I've doubly shaded this middle piece. And so to counter that, I want to subtract out one instance of since it was shaded twice, if I just subtract it out once, then I would get the probability that we're after, which is the probability of E or F. So here is a rule, and if you're ever calculating the probability of E or F, one of the first things I would go to is this tool, this formula. And we'll look at some examples here in a second. The other one is the complement of an event, which is denoted E complement. It's always the case that if you add the probability of E plus the probability of its complement, you're going to get 1, another version of it. The probability of a head is equal to 1/2. The probability of not a head, well, in this case, it means the probability of a tail is also 1/2. So the probability of an event plus the probability of its complement will add up to 1. And that'll work in every situation. All right, let's go to some problems. I think I'll focus more on the empirical probabilities since we are in statistics, but we'll do some games of chance as well. Okay, it says verify that this is a probability model. Okay, for that, we need two things. We need to see that all the probabilities are numbers between 0 and 1. Is that the case? Check. And we need that when we add up all those probabilities, we get 1. And when we sum all those up, 46.61, 0.95, the sum does in fact equal 1. So that's how you confirm that this probability model, or this is a probability model. You have a listing of all the possible outcomes with their corresponding probabilities. All the probabilities are between 0 and 1, and the sum of the probabilities add up to 1. This is a family structure in 2013. 2 married parents in their first marriage, just under half the families are like that. 2 married parents, 1 or both remarried, 15% of the families are like that. Single parent families, about a third. About a third of families in the United States. Single parents. No parents at home, 0.05. Okay, let's go ahead and answer these probabilities. Whenever you see what is the probability, what is the probability, what is the probability, then you know that the answers have to be between 0 and 1. So you're looking for a number like that. A randomly selected family with at least one child younger than 18 years of age in 2013 had, okay, 2 married parents in their first marriage. 2 married parents in their first marriage. So you just read it. This is not a frequency distribution because they didn't actually give us the frequencies and ask us to calculate the relative frequencies like our earlier example. They actually give us the probabilities. So all we have to do is read the table and pick out the right probabilities. Interpret, 46% of all families have 2 married parents in their first marriage. So, and I'm not going to interpret all of these, but notice the probability is the decimal number, and when we interpret it, we use the percentage number. Okay, what do you get for C? What is the probability that a randomly selected family with at least one child younger than 18 years of age in 2013, okay, and then here comes the event, had 2 married parents? Anybody want to take a shot of that in the chat? Okay, yes, you add those two together and you get 0.61 because both of these involve 2 married parents. So you're going to just take those two probabilities up there at the top and add them together. What is the probability that a randomly selected family with at least one child younger than 18 years of age in 2013? So all of that verbiage up at the top is just say, okay, refer to that table up there again, had at least one parent at home. Now, because this one says at least one parent at home, and this idea of at least one can use the complement rule. Probability of at least one in any context is equal to 1 minus the probability of none. So in this case, it's easier to take 1 minus the probability of no parent at home than it is to sum up all the other 3 probabilities. But you can get it in one of 2 ways. You can sum up these 3 probabilities to get 0.95, or you can take 1 minus this, because we know the sum of all these add up to 1. At least one parent would include a single parent or married parents. So those 3 categories. And then you have a 2-way table, 2-way frequency table. And we'll end on this one here. You have, this is an empirical setting, but this is called a 2-way table because we have 2 variables going on. We've got the number of children at home, and then we have who works in the family. Is it the husband only works? Is it the wife only works? Or do they both work? And we looked at families here where we had at least one working spouse. Number of children in the home, 0, 1, 2 or more. So here is the overall sample size of this study, 1,700. All right, let's go through these probabilities. The probability that for a married couple selected at random, both spouses work. So there's no reference here to the number of children in the home. It's focused only on the families, the family structure, both spouses work. So both spouses work. It would include those families that have 0 children, those families that have 1 children, and those families that have 2 or more. All families where both spouses work, there are 1149. And that's out of the total number of families surveyed, 1,700. Then we would want to convert that to a decimal. And I'll round the decimals off to 3 decimal places.